So now we're going to talk about separable image transforms. So separable image transforms are those that are quite distinct from the general linear transforms that we've looked at before. Well, I say quite distinct. In fact, they are a subclass of general linear transforms. So the thing that's true about the linear transforms we've looked at so far is that, and all linear transforms will be, first of all, some sort of form of or algorithm to go from transform space, so these are the coefficients of transform space, back to image space by a weighted summing of the basis images. And the way that we get these coefficients, as we've seen, is given by the forward transform. And in both cases, so this inverse transform we've seen can actually be a fairly surprisingly simple type of calculation. It simply involves blending the basis images together with different scalar weightings on each of those images. To go into the transform space, we have looked so far at this calculation over here, in which we take, so this is an example image we're using of just 4 pixels, and of course different images will give us different results, but the images are independent of the basis functions. The only effect, just to remind you, on the basis functions or the basis images that this image will have is the size. So if the size of this is bigger, then these basis images will be bigger and they will be more numerous. But the basis images themselves, the way they're defined, comes from specific transforms, or would be one set of basis images for which consists of oscillating sines and cosines for a Fourier transform, and other basis images that we'll look at shortly, which are associated with different transforms. So when we move from image space into transform space, we've seen that the algorithm we use is to do the inner product, matrix inner product between this image and each of the basis images in turn. But so we've got 4 basis images here, but if we were to scale the size of this image, we would get 2 effects happening. First of all, if we make this, let's say, 3 by 3, so we'd have 9 pixels in this image F, we would first of all get these basis images being bigger in each dimension. So this will be 3 by 3, that'll be 3 by 3, this will be 3 by 3, this will be 3 by 3. Plus, we will have more basis images because, as we've seen, the number of rows and columns for the basis, for the transform space, which is large K and large L, those are generally equal to large M and large N. So we get, we would have, in short, if we made this a 3 by 3 image, we would get 9 basis images, and each of those basis images is going to have 9 pixels. So the effect that this gives is that the scaling of computing the image transform, so going from image space into transform space, scales in such a way that if we had a square image, so consisting of large n rows by large n columns, so I'm using one variable now, which is large n, then the number of basis images will also become n squared, and each of those will also be of size n by n. It means that the computation, approximately speaking, scales to go from image domain to transform domain, scales as n, large n, to the power of 4. So as we increase the size of a square image, we find that we get a 4th power increase in the number of calculations we need. And so this becomes unsustainable if you have to do many transforms. For example, if you have to do this at video rates, then although you could do it with modern computer hardware, you pay a cost in terms of energy expenditure. So The idea behind separable transforms is that you get a reduction in the computational cost. So let's see how this works. So first of all, we've seen that the basis images, generally speaking, will have this form. So little b as a function of kl, m, and n. So we have 4 variables here. Well, if we can express the basis images as a product of 2 separable functions, each of which is like a series of rows, because you've got one index here. So as you fix one basis image, remember we fixed 1k and 1l. As we fix each of these, we have the product between 2 things that vary as a function of m. Well, one thing that varies as a function of m, another varies as a function of l. So these become a bit more, and this is why separable is useful. This becomes a bit more like a row and column type of operator. And so you see that I've got a subscript here of little r and little c. And generally speaking, the transform space representation can be performed by doing matrix multiplication. Remember, we made the distinction between following matrix algebra, following the rules of matrix algebra, and doing this other thing, which is called the matrix inner product. Here, what we're doing is computing, we're moving from image space into transform space by treating the image f, which is an array of pixels, as a matrix, and operating with that matrix on a pre-multiplying matrix that's of the same size as, or as appropriate dimensions to match for matrix algebra, and then take that result and pre-multiply that by AC. Okay, so we've got these 2 separate matrices that we apply to f. And again, I'm going to stress the point that here we are doing matrix algebra. So we are treating an image, which is an array of pixels really, as being a matrix, and that is unusual. So although it's a very important concept to, it's very important for separable transforms to be able to do this, this is very unusual because in computer vision, let's say, because what you typically want to do is to preserve the spatial structure and exploit the spatial structure with neighborhood operators on incoming images. Hence, the success of convolutional neural networks in building these image interpretation systems. But in this particular case, we treat the image or array of pixels as a matrix, and we do this. We do matrix multiplication. So there is a special case in which we'll look at where that matrix operating on the rows, AR, and the matrix operating on the columns is the same, in which case we get something like this as our mapping from image space into transform space. So V is equal to A transpose. So let's look at an example of doing that. So here is an example, and what you should do is try this using f as in the previous example a few slides back. So f will be our input image, our little 2x2 input image, arbitrary input image. So try using that and applying or performing this calculation using matrix multiplication. So use matrix algebra multiplication. Let's shorten that to multiply. Okay. Now this particular array here matrix here that's used for this operation is the same for the pre-multiplication and post-multiplication, except the pre-multiplying matrix would do a transpose of that. Really important. This is a special case of a matrix that has been designed to be used. I'm not going to give everything away, but it's related to these basis images here. So here in this calculation, the basis images are not explicit; they are implicit to the calculation. But what you need to do is to do this calculation and see what result you get. If you do this right, big hint, you will find that you get the same result we had back here. You'll get this thing as well. So in other words, this calculation, which is separable, is equivalent to the calculation we did back here between f and the explicit basis images. Okay, so somehow the basis images are buried inside this thing, and we'll look at how to get those out in a little while. First, I want you to note something about this matrix. So if you have a look at this matrix is what's called an orthogonal matrix. And so here, the rows of this matrix are orthogonal to each other. If you treat each of these as being a vector in a two-dimensional space, then these two vectors are orthogonal. If this matrix were applied to, let's say, a 3x3 image, you'd have 3 rows and 3 columns. And there again, if each row was orthogonal to every other row, then you would say that that was an orthogonal matrix. Orthogonal matrices have the very nice property that their conjugate transpose is their inverse, so they are trivial to invert. And this particular matrix also has the nice property that its transpose is equal to itself because of symmetry. So when you do a matrix transpose, what you do is you swap the row and column indices. And so when you swap the row and column indices, the diagonals stay the same, but these two will swap and they're identical, so this thing stays the same. And therefore, this matrix is easy to transpose, easy to invert, and we'll use that later on. Now, so you need to do these 2 steps. The final thing here on this little exercise asks you to recover the image from its transform values, and that should be you can do that using matrix algebra. So if we have this, let's go to our board scene, and I hope this currently is working. And let's make this nice and fat. So let's say that we have this is the what we have is v in terms of make that fatter, right? So what we have is that v transform space is equal to a by f, there's our image, times a transpose, and just remind ourselves that we have a particular form for a. However, using this, we can invert the left and right hand side. Well, we can pre-multiply this by a inverse to get rid of that a there. So we can do a inverse times v will be equal to a inverse a times f times a transpose. And if we post-multiply this by a transpose inverse, then we would have a inverse v equal, a transpose, inverse is equal to a inverse a f a transpose minus 1. Okay, now this will just be the identity matrix, and that's multiplied by, so this is 2 by 2 ident matrix, and then this here is also just going to be the identity matrix, so this is going to be I. Okay, so we end up with, and that's just equal to f, and so we end up with f is equal to, now we said that a was its own inverse because this is an orthogonal matrix, so, and also it's symmetrical about the leading diagonal. So a inverse is simply, so this thing here is equal to a transpose is equal to a, And this thing here, so A transpose is just going to be A, and the inverse of that we know is going to be A transpose, which is A. So this is also equal to A. So we get F is equal to A V A. So for those of you who like food, fava, of course, type of bean. So there we are on food again. So that gives us the expression we would need to move from transform space back into image space. So try that and make sure that it works as expected. Okay, so to be clear, if you try that, what it means you're doing is you're going to go back to this thing here, transform space, and apply that particular definition of A back. And what you should find is that you get back to image space 1, 2, 3, 4, as we had up here. Okay, now the final question in this little exercise is to deduce the basis images of this transform. And that's actually surprisingly easy. Why? Now, remember we had another thing that we said about the inverse of the transform, which is this. So this is applying a weighting to each of our basis images. This is a scalar. Yeah, so this is a scalar that's pre-multiplying a 2 by 2 array. And we've got 4 of these, in principle, of these basis images. And so we take each of those basis images, which again are shown back here, and we apply these weights here to blend the basis images together, and we reconstruct this. But if you look at this expression again, one of the nice things about this expression is that if any of these scalar values is 0, then what you get is 0 if all of the scalar values here are 0, you get F being just equal to 0, 0, 0, 0. If everything is 0, but one of these values is set to 1, then what F automatically becomes is the basis image corresponding to that one value of coefficient that's set to 1. And that means, and this is where there's often a lot of confusion and a lot of people find it difficult to understand. But if you, to answer this question, if you create an empty transform space and then set one value at a time to be equal to 1 and all the other values 0 in transform space, then if you apply an inverse transform to that empty transform space, you will automatically get the corresponding basis image. So you need to do that because it does work. And the way you do that is you literally make, so to recover basis images, given a transformation specified by, I should say, inverse transformation by F equals AVA, then in fact, to make this general, let's use AVA transpose, just in case we don't have something that is symmetric. Then simply, and I mean simply, it really is that easy, set v equals 0, 0, 0, 1, for example, and compute inverse. F will then be, again, for example, B 1, 1. Okay, why is that? Because here, this coefficient here is V1, whoops, is V1, 1. Okay, so to recover B0, 1, so what we're doing here is we're saying, let's pretend we have a transform as defined by this separable function. And often in software engineering, or let's say in using transforms, you're going to be given a library that executes the forward transform and that executes the inverse transform. So you can't explicitly see the basis images. So to get at the basis images, what you can do if you want to understand what they look like is you make an empty transform space. Just invent one. You don't need an image to do this. You just assume you start from transform space, but make it all empty and set one value at a time to 1 and everything else to 0. And when you set each value to 1 in turn, you compute the inverse transform, and that will be the basis image that's embedded in that transform algorithm. So think carefully about that interpretation. It gives you a huge amount of insight into things like the discrete Fourier transform and other types of transform that we're going to be meeting later on, very soon in this particular lecture.